Okay, so let me just quickly return to the Bicommutant theorem to make some closing remarks and some corollaries. So first let me just reformulate it in a way which is perhaps a little bit more convenient. So suppose A in B of H is a sub C star algebra, then the following are equivalents. One is that A is its strong operator topology closure. The other is that A is its weak operator topology closure, and the third one is that A is its bicommutant. Right, and the way that we defined it, this is what it means for A to be a von Neumann algebra. And of course this follows from the formulation that I had on the other pencast, because under the same assumptions all the sets to the right are equal. So let me just point out a useful way of thinking about this, and that is suppose F lies in B of H is closed under star. So what I mean by that is if I take all the elements in F and star them, I get exactly the elements in F. Then F double commutant is the smallest von Neumann algebra containing F. So maybe you should think a little bit about why is there a smallest von Neumann algebra containing F, but B of H is already a von Neumann algebra containing F, and since we're formulating it using something about being closed in a certain topology, you can always sort of intersect all the von Neumann algebras containing F, and that will give you the smallest von Neumann algebra containing F. But that's not necessary if we have a concrete F. We can just generate the smallest von Neumann algebra using F's bicommutant. And I mean, there is a little observation behind this which explains where this condition comes from, and that is that, you know, if F star is F, then also F prime star is F prime, etc. Because since if F is closed under taking adjoints, we have that Ts is St for all S in F, and T in F prime. I mean, what I've written up this far is just that T is in F prime. But the point is that since taking stars on the S's does not change anything, I can put stars here, and this remains true. Right? So then when I star everything, I get that St star is T star S. So T star actually lies in F prime as well. Right? So the point is that if I know that F is closed under taking adjoints, so is F prime, and so is F double prime, and so on. So that explains to me why F double prime is closed under taking adjoints, and hence I can use F double prime in the theorem because it is a C-star algebra. Right? It's a C-star algebra because it's closed under taking stars, and that's not obvious from the other axioms. So it's a C-star algebra. All the other axioms for being a C-star algebra will be automatic. For instance, if I have two elements that both commute with everything in A, the product also commutes with everything in A, and so on. So this sort of is just a reformulation of what we've already done. So a slightly more advanced application of this has to do with the polar decomposition. So let me just remind you what that is. So this is something we did in chapter 12. So suppose T is an element in A, which is a C-star algebra lying inside B of H. Then there exists an element P coming from A and an element V coming from B of H, so that the following observations hold. So T is the same as V times P, and P is positive and it comes from A, and the kernel of P, the kernel of P is the same as the kernel of V, and V is a partial isometry. So, I mean, this, from a point of view of C-star algebra theory, is a little bit disappointing, because I'm allowed to make a polar decomposition. I mean, I can write T as a partial isometry and a positive element, but I have to leave A in order to obtain my V, right? So there's not a statement saying that V can be chosen from A, because that's not even true. But as a nice corollary to the Bicommutant theorem, we in fact have that if A is a von Neumann algebra, then P and V may be taken in A, right? So, I mean, it's clear that P is in A, but I'm mentioning this for completion, for completeness. So, to prove this, I'm sort of dancing around a little bit the lack of uniqueness here. So, a polar decomposition, I think most people would just mean that to be that T is written P times V, where P is positive and V is sufficiently like an isometry. But I need, for the uniqueness part of this, I need that V has the same kernel as P, and that's not strictly necessary for this to work. But I want to work with that particular V that has the property that its kernel is the same as the kernel of P. And as you'll see in a second, that's how I prove that V is in A. So, I mean, the polar decomposition is only unique if you put in this extra condition that I have here. And so that's the polar decomposition I'm talking about, and that's the one I want to claim I can realize inside the von Neumann algebra. So how are we going to do this? So really my goal is to convince you that suppose we take some S that lies in A prime, then I want to convince you that Vs is the same as SV, right? And if I've done this, then I know that V is in the bicommutant, and the bicommutant is the same as A, because by assumption A is a von Neumann algebra. So this is really all I need to do. So fix some X coming from H. I'm going to try to see what happens if I apply Vs to Px, and if I apply Sv to Px. So what can I do about this? So Vsp is the same as V P S, because I know that P comes from A and I know that S comes from A prime, so they commute. And VPS, of course, is nothing but TS. I need to remember my X here, so that just gives me TSX. Right, but I could do something similar on the other side, because VPX is STX, and T comes from A, right? So this comes from A, this comes from A prime, so they commute, so that gives me TSX, so that gives me the same thing, right? So thus Vs is the same as SV on elements of the form Px with X in H, right? And by continuity, also on the closure, right? So I want to convince you that Vs is the same as Sv, and I've done this on the image of P. But note also that Vs is the same as Sv on the kernel of P. So why is that? So we fix some y coming from the kernel of P, which I recall is the same as the kernel of V, right? So obviously SVY is going to be 0, because y was in the kernel of P, and then it's also in the kernel of V, and so when I apply V to it, I will get 0. But note also that Sy is in the kernel of P, since when I apply P to Sy, I get the same as Spy, because this is in A prime, this is in A, and of course Py is 0. Right, so then we get that Vsy is 0, because this now is in the kernel of P, which is the same as the kernel of V. So thus Vs and Sv agree on the image of P, and it also agrees on the kernel of P, and we know that these two subspaces are complementary subspaces adding up to H. I need to take the closure here, because this is a general thing that we can subdivide H into the range of T and the kernel of T star, right? But P is positive, hence self-adjoint, so I can do this with P. So this gives me that Vs and Sv are the same, and so they commute, and so V lies in A double prime, so V lies in A double prime, and that's just A, proving the claim.